So I will, as the other speakers, before I will start with the scientific work, I will start introducing our group a little bit. So I'm a member of the Photonics Research Group at Ghent University, which is within the Department of Engineering and Architecture at Ghent University. We're also an associated lab of IMEC, which means that we are making heavily use of the facilities of IMEC, and that will come back throughout the talk. You will see that. So you're working basically on photonic integration and systems on a chip, but yeah, so in this case on silicon chips, on a somewhat smaller scale than what Heidi just explained. It's all focusing on silicon, we call it Silicon Photonics, but as you will see in a minute, is going a little bit broader in the meantime than just using Silicon Photonics waveguide. And we are working also on a lot on, and that will be the main topic of this talk, on enhancing this material, this waveguide platforms with new materials like 3-5s, ferroelectrics, graphene, and so on. We're working on a pretty broad application field. High-speed telecom and datacom is, of course, the classical application field for this kind of chips. But in the last 10 years, like sensing for life sciences, both in the visible and the mid-infrared, optical information processing, quantum optics, and so on, are all actually being more intensively being investigated in group than the classical telecom applications, which have been shifted a little bit more to industrial research. So in total, there are 9 professors in the group, and those are, yeah, these are my colleagues, let's say. And then, yeah, the field that we're covering is quite broad. You see some of us are mostly looking at component size, device size. That includes myself, Professor Kuik, Roelkens also, while others are looking more at applications, like Roel Baats is focusing a lot on sensors for life sciences. Nicola is looking at biophotonics, NUV photonic ICs. Geert is looking at lasers, very fast lasers for optical communications. And Peter and Wim are looking at more computing types of applications. But the common theme for all of that, as I already mentioned, is Silicon Photonics. And so what is Silicon Photonics? It depends a bit on who you talk to, but as we define it now, it's basically the implementation of high-density photonic integrated circuits by means of CMOS process technology in the CMOS fab. So it's not, as I already mentioned, not necessarily silicon waveguides, but the core is that ultimately the process that and the chips that we are developing, it should be possible to fabricate them in a classical CMOS fab. It doesn't mean that we do everything already in a CMOS fab. Some of the more advanced processes, yeah, at this point are still too adventurous, let's say, to move to real fab. But ultimately, you could dream of moving these processes there. In the past, we focused almost exclusively on silicon waveguides. So with this kind of cross-section, like a 500 by 200 nanometer strip of silicon on silicon oxide. And then later we also had contacts on top of that and could make active functionality in that. But of course, the silicon waveguides are limited in wavelength range that you can address. At the lower side, that's the transparency of silicon, of the bandgap of silicon, which is about 1.1 micrometer in practice. And then at the upper sides, it's actually the absorption of silicon oxide. Silicon oxide starts absorbing a little bit above 3 micrometer, which limits, yeah, far infrared or mid-infrared and far infrared applications. So that's why we moved to other types of waveguides also more and more. So we're using a lot of silicon nitride, both for visible and near infrared of telecom applications. Germanium waveguides. In this case, so germanium has a higher index than silicon, so you can make germanium on silicon waveguides, so which are transparent up to 10 micrometer for addressing, for example, gas sensing applications in the mid and mid-infrared. And then if you want to go to very short wavelengths, then silicon nitride also starts absorbing, and that's why our chair today, so Professor Le Thomas, is starting to look at aluminum oxide waveguides, which should be transparent in this in the UV wavelength range, and so you could also address sensing applications in that wavelength range. But the basic platform is still, for many other projects, is still the silicon on insulator platform that is now fully fabricated at IMEC in the fab, and which is also publicly available, and which has waveguides, of course, so you can make complex filters on chip. There are grating couplers to couple light in and out of the chip. You can do that with these grating couplers, but actually also at the side with these edge couplers. There are germanium photodetectors. There are modulators, ring modulators, Mach Zehnder modulators, and so on. So in theory, you can do everything with this except for lasing. I mean, the source is not in this platform for the moment. In practice, there are quite some limitations still, and certainly for novel type of applications. So silicon is great, but it has an indirect band gap, so you can not make an efficient emitter directly on the silicon platform. And it has a cubic lattice, so you have no second order nonlinearities, means that you have no efficient electro-optic effect, and also doing nonlinear optics on the chip is not so efficient. So that's why I believe we need integration with new materials, and we are looking at a whole bunch of new materials, as for example ferroelectrics like BTO, lithium niobate, PZT, for pure phase modulators and second harmonic generation, graphene and other 2D materials for intensity and phase modulators, colloidal content nodes for light sources and single photon emitters, and direct bandgap 3.5 semiconductors for efficient light emission. So I mentioned them as the last one here, the 3.5 semiconductors, but actually this is more than half of the work in this field is on the 3.5 semiconductors. That's really the biggest activity. But from my side, personal, I'm working on all four of these materials. So starting with the ferroelectric materials. So there, in a collaboration with my colleague Jeroen Beekman from the LCP group, also at Ghent University, we developed a process to integrate different types of materials like BTO, lithium niobate, and PZT, basically on any substrate. So typically, I mean, in itself, that's not new, and there's a lot of people that depositing, for example, PZT on silicon. But they always use a platina buffer layer to grow that PZT. And platina, of course, is not very interesting in optics applications as it's very lossy. So the key breakthrough here is that so the team of Professor Beekman found an approach to overcome this platina layer. They actually developed this lanthanide buffer layer, which after annealing forms a crystalline, polycrystalline layer, which then can be used both as a buffer for diffusion of the material, but also as a seed to grow then polycrystalline PZT or lithium niobate or BTO on top of that. So here, for example, you see a silicon nitride waveguide, but then here locally being covered with PZT. And then we see if we apply contacts, so we have here we have a ring resonator with an outside contact and an inside contact. So we can apply an electric field over this material. So if you look in more detail, so you have the waveguide over here, then the PZT is on top, and we have a field applied here in a PZT. And given that PZT has a strong electro-optic effect, so basically we change the reflective index by applying this field. And we see this reflected in the fact that the resonance of this ring resonator shifts with applied field. So we could demonstrate this for the first time that this actually works in waveguide type of configurations, and that we really have a pure phase modulation in this case. And now we're working further on this to improve the effect, to improve the configuration of these structures. We're also working a lot on 2D materials. This is in strong collaboration with the 2D material group at IMEC. Most of the work has been focusing on graphene-based electroabsorption modulators. So it's a bit a similar structure as I just showed. So we have a we have a waveguide, for example, over here. So this S-band, it's like an S-shaped waveguide where we couple in over here and then couple out over there. There's a piece of graphene here. Of course, you cannot see it. And then we apply a field between on the one hand, the metal contact on top of the graphene, and on the other hand, a metal contact on top of the silicon below. And that induces a field in the graphene, shifts the Fermi level, and so shift also the absorbance of the material. And doing this, we could show that we can indeed make high-speed modulators with these materials. So there is, scientifically, I mean, this is maybe not so exciting, but it was really a lot of work in getting the processing right, being able to do this on more than one device in a sort of reproducible way. We are also starting work on, instead of using graphene, using other types of 2D materials, with the idea of maybe also being able to change the refractive index, and so do not have mostly an amplitude variation like we have with graphene. It's not fully correct actually, but basically avoiding the amplitude modulation we have with graphene and focus more on pure phase modulation. We hope, and it also has been shown by some authors, that we can do that with, for example, tungsten diselenide and molybdenum disulfide and so, but that's still under research. A result that we already did publish, and actually this was in strong collaboration with the England group at MIT. So it's work from a postdoc in our group, Frederik Peijsens. So he deposited tungsten diselenide, a piece of tungsten diselenide on a silicon nitride waveguide. And it has been shown that some defects in these tungsten diselenide films can act as single photon emitters. And what he has, I mean, that in itself was known already for a few years, but what he demonstrated for the first time was that he was able to couple the emission of this single photon emitter in the 2D material to the waveguide, and then picked it up from the side, and he could show, for example, anti-bunching, and demonstrate that this was truly a single photon source. Colloidal quantum dots. This is based on a long-standing collaboration with my colleague Zeger Gens, and now more recently also Peter Gerhardt at chemistry department of Ghent University. So they are making these colloidal quantum dots, mostly cadmium sulfide, cadmium selenide. And in the meantime, also other materials like indium phosphide based and lead sulfide and so on. And so these are quantum dots fabricated in solution, and the nice thing is that by controlling their composition and their dimensions, you can basically control the quantum confinement and hence also the color of the emission, so the wavelength of the emission. So in principle, this could serve as an alternative gain material, mostly in the visible, for the classical 3-5 semiconductors that are grown epitaxially. In principle, it could be very cheap, and also their properties can be controlled in solution, and can very easily be controlled from one device to another device on the chip. We had to work very long before we got, for example, actual lasers from this, and so we needed a lot of optimization of the material properties themselves, but also on the way we process them. But 3 years ago, actually, for the first time, we could demonstrate lasing from structures like this. So we had a stack of the red layer here is the quantum dots, and these quantum dots were sandwiched between 2 layers of silicon nitride. We fabricated a waveguide from that and then etched the grating on top. And so this forms a cavity, an optical cavity, where this material then, where the quantum dots then can provide a gain under optical pumping, and ultimately we saw lasing. And depending on the grating period, you see lasing at different wavelengths. So this means that this material is indeed good enough to show lasing. These were the first, let's say, integrated photonic lasers based on this type of materials. We are working now further, working towards electrical injection, towards CW lasing, and so on. And also in parallel, working also more towards quantum optics applications, and that's shown in the right picture here. This work from Lucas Elsinger, who will graduate next week, and was published in Nanoletters. What he had here was a very small pillar of lead sulfide quantum dots. Ultimately, we would like this to be a single quantum dot, but we're not that far yet. So here it's like, I think, 10 to 50 quantum dots in a very small pillar, embedded in a gold plasmonic antenna, which enhances the emission of these quantum dots and enhances the coupling towards silicon nitride waveguide below. So these quantum dots are pumped from the top. To ensure that the pump light is filtered, we had a very strong filter over here. Then we had a grating demultiplexer to couple light from multiple, no, sorry, to split the light into multiple wavelength channels. And then at the end, we had superconducting single photon detectors fabricated by a partner, Single Quantum in Delft, which allow basically to detect single photon events. So this chip was characterized, and we could show that indeed we have enhancement of the lifetime, so decrease of the lifetime of the emitters due to this antenna, and that actually, in principle, we should have the possibility to do single photon characterization with this chip. So single photon emitter characterization, but we're not there yet. And then I'll switch to the 3.5 lasers. So we have basically two approaches to, well, so first, what is the problem? So we have this Silicon Photonics platform, which looks a bit like that. So on the bottom here, you have the silicon waveguides and active devices. Typically then after processing, there's a thick layer of oxide on top of that and also all kinds of metals. So the question is, how can we get lasers in this platform? And so the first solution is transfer printing. So we etch basically a gap in this oxide, and then we print 3.5 materials on top of that in these cavities. In this printing, that's a technique called transfer printing. The technique as such is well known in literature, is well described, and is also commercialized by a company called Excelleprint. So you use a polymer, a PDMS stamp, to pick up samples from a source substrate. These samples are already pre-patterned, and then you use the same stamp to print the coupons, so the material you want to print on the target substrate. If you look in a little bit more depth how it works with these 3.5 materials, basically on your source substrate, you have the 3.5 device layer and then a release layer. You first pattern the device, you encapsulate it with photoresist, and then you remove the release layer. So you under-etch the release layer such that the actual device is free hanging. Then you can come with your stamp, pick it up, and push it on your target device. And it actually works. So we have a tool for that, a small lab tool for that in Ghent, but ultimately we can move this to very large tools. It has been demonstrated on for example, on panels, very large scale. This is an example from the team of Ghent University. So he fabricated tunable lasers. Well, his students fabricated tunable lasers by integrating the 3.5 amplifier, so a semiconductor optical amplifier, on a chip containing tunable mirrors fabricated from these ring resonators. And he could show lasing. Okay, there's some mode hopping over here, but it's not so important. But he could show lasing, and he could actually, I don't have that picture here, but you could tune the emission wavelength over a very wide range, over more than 50 nanometer, I believe. Another example from the team of Prof. Bart Kuiken, he showed integration of such amplifiers on silicon nitride, which is then important to for high power applications where silicon suffers from to photon absorption, for example. These results were published in Optica, just beginning of this year. And for example, he showed also lasing and amplification. Another example, so these are photodetectors fabricated. So this is the source. So this is before printing. Then you come with your printer, you print them on a target. So these are silicon waveguides with then these photodetectors printed over here. And this is the source wafer after printing. So this seems to work now, is maturing, and we can actually use this for a lot of materials. So not only 3.5s, but also lithium niobate, graphene, colloidal quantum dots even, and so on. The second method for 3.5 integration I'm working on then together with the team at IMEC is direct epitaxial growth. So this is the ultimate dream to be able to do this. So instead of having to transfer from a 3.5 wafer to the silicon, you directly grow the 3.5 on the silicon. So something like this. The challenge, of course, is that all the 3.5s that we are interested in, so the 3.5 materials with a direct band gap, they all have a lattice constant which does not match silicon. So typically it's a larger lattice constant. So if you want to do this, if you try to do this growing 3.5 on silicon, you typically get a lot of threading dislocations, for example, misfit dislocations, which are disastrous for your device. And some examples here. For example, you have microtwins, you have these threading dislocations. So this is the growth interface between silicon and 3.5. So these dislocations moving up, and then they're detrimental for the operation of the device that probably is located here. That's why, so the EPI team at UGent-imec developed an approach, and it's the main collaborator there is Bernadette Kunert. So we're starting from narrow ridges etched in silicon. And so we're talking about ridges here of a few tens of nanometer to a few hundreds of nanometer. These are planarized. And then this is the trick. So we etch the silicon with KOH such that you here end up with the 111 crystal planes. And this is very important to suppress antiphase domains. Yeah, I don't have time to explain this, but I'll gladly explain later if requested. So then we start growing the 3.5 material, and now if you have a threading dislocation, it will move along the 111 planes, and so you see it's not going upwards, but it's moving sidewards, and if the trench is narrow enough, it will be blocked at the sidewalls. So if the original trench, or if the original silicon was high enough, then all the dislocations will be trapped, and then you can further grow out of the trenches, and this will be defect-free material. This actually works. So this is an example of a temp pitch of such a material. So it's gallium arsenide grown on this narrow trench. The trench, you cannot see the defects here, but I will show some pictures in a minute. So this is full of defects, but the top is very clean. There's no defects over here. You have very clean quantum wells. So why does it work? Well, because these threading dislocations are moving along these 111 planes, both in that direction and in that direction, you see that they are moving along the 111 planes, and both directions will be trapped. So the only thing which will not trapped is planar defects, which are moving along the 111 plane over here. These will still enter your, but they are less detrimental, and we think we can, with cleaning and so, we can actually suppress them. So here you see that it indeed works for a 100 nanometer wide trench. You see that all the defects are trapped in the trench. So this is the height of the trench. It's 100 nanometer wide, so they're all trapped at the interface. Well, here this is for a 200 nanometer trench, and then you see some dislocations are going out a little bit higher. And if you would make this picture for an even wider trench, then some dislocation would certainly go upwards. The funny thing is that you can grow all kinds of shapes, but till now we are focusing on the more regular shape, this rectangular shape, which supports nice TM and TE modes. The TE mode has the nicest overlap with the quantum wells, so we suppose that's the one which is lasing. And indeed, it is lasing, so by etching a grating on top, we could show lasing under optical pumping of these devices. We can control the wavelength again. Later, we also made devices by depositing a metal grating on top. So instead of etching the grating, we just have a metal grating defined by e-beam lithography. And so this metal grating supports two block modes. One block mode will be very lossy, as the one which is localized below the grating, but the other one, which is localized in between two grating periods, will have actually pretty low loss, and that one is lasing, we believe. We're also working on, thus far, simulation of coupling of these structures to silicon waveguides, because that's, of course, ultimately the dream, that we can couple the light to a waveguide next to it. I will not go, in view of time, will not go in detail here, but we optimized the structure and could show that, in a few tens of micrometer, you can couple all the light from the 3.5 to the silicon waveguide. So the outlook for this this work is, this is the context of a new ERC project, where we will focus on electrical injection, in particular of micro lasers, and we're also looking at single photon emission of quantum dots grown into these trenches. So this brings me to the summary of the talk as a whole. So I believe novel materials clearly show prospects for performance beyond what is currently available in existing Silicon Photonics platforms. These type of modulators have been demonstrated by several groups, and several are now also in a spin-off phase. There are spin-offs from Harvard, from IBM, working on lithium niobate and BTO respectively, for example. Graphene devices are also maturing rapidly now, and 3.5 integration through transfer printing is also really ready for the main stage. Through EPI is still very much research phase, but I think we can expect some exciting results there in the coming years. Overall, I think there is still a lot of room and need for further improvement in this field as a whole, both on the fundamental building blocks and even the materials can still improve, but also then towards new applications enabled by these new building blocks. And that's it. I still have to acknowledge all my colleagues, but most of them already mentioned during the talk, and of course the funding. Thank you.
Thank you, Dries.